To give you more practice in this kind of thing, here's another example. The magnesium-silver cell. Answer these questions yourself before you proceed with the video. Make use of your table of standard reduction potentials. Clearly, the magnesium is going to be oxidized and the silver ions reduced. We can see this by the fact that if we follow this reaction, it forms a correctly written C shape. You know, when we write C, you should write it like that. You shouldn't write your C's this way. And so we call this a forward C. And when you can read the reaction from the table in a forward C, then you know that the reaction is going to be spontaneous, and this is what will happen in a voltaic cell. Right, so clearly the reaction directions are going to be as shown there. So magnesium is going to be oxidized. It's going to change into magnesium ions, increasing the solution concentration because magnesium ions are soluble, so they'll move away from the magnesium metal electrode and go into solution. And the silver ions that were in solution around the electrode are going to be reduced. They're going to gain electrons and so precipitate into silver metal, which is insoluble. What is the E cell, the standard electrode potential of the entire cell? Remember, we find it by finding the difference between the cathode's standard electrode potential and the anode's. So what is the cathode? The cathode is the silver cell because that's where reduction happens. The electrode potential for the silver cell is 0.8. And then we have the anode. The anode is the one where oxidation happens. It's the magnesium electrode. And it has a standard electrode potential of minus 2,37. So our equation reads 0,8 minus 2,37, and we know that a double negative makes that to be positive, and so what is the answer? 3,51 volts. And here's some more practice for you. Answer these questions before you continue. Pay particular attention to writing the oxidation and reduction half reactions, and especially the entire redox reaction, making sure that it's balanced in all respects. Pause until you've done this yourself. So we read the equation in a correctly formed C shape, and from that we see that aluminium is going to be oxidized to aluminium ions, mercury ions reduced to mercury. We know that oxidation is happening at the anode and reduction is happening at the cathode. We make use of this equation to help us to find out what the electrode potential of the entire cell will be, and you should find that answer. But I want to stress the oxidation and reduction half reactions, and particularly the redox reaction. Start with the oxidation half reaction. We read this backwards as always. Aluminium gets oxidized to aluminium ions. We can see that the oxidation number is rising, and that is accompanied by a loss of electrons. In this case, 3 electrons are lost for every aluminium atom that is oxidized. Then we have the reduction reaction, which as always in this table we read forwards. Mercury ions gain electrons to form mercury. We can see reductions happening because the oxidation number is decreasing, or we could also notice that because electrons are being gained. But now the important thing to realize is that not as many electrons are lost as gained if 1 atom of aluminium were to react for every 1 atom of mercury. Now, there have to be just as many electrons given as taken, because where else would the electrons go to or come from? And so, the ratio between the oxidation reaction and the reduction reaction has to be adjusted until as many electrons would be released as taken in. Try to do that yourself. I hope that you've realized that we need to have the ratios of oxidation to reduction in the ratio 2:3, or put in a very simple way, we must multiply the top reaction, the oxidation half reaction, by 2 all the way through, and the reduction by 3 all the way through. So how then would we write this final equation? Make sure that you do multiply every single element, every single unit inside the top equation by 2 and every one by 3 in the bottom. Then we put the 2 together, and this is the redox reaction we come up with. 2Al plus 3 mercury mercury ions gives 2 aluminium ions plus 3 mercury. Only if they react in this ratio will as many electrons be given as taken. In other words, the electrons will be balanced. And then here also is the final answer. 2,45 volts would be the potential difference between an aluminium and a mercury electrode under standard conditions. Here's another example for some more practice for you. First, answer the questions yourselves. We read the reaction in a correctly formed C. We read the oxidation half reaction backwards. H2S is oxidized to sulfur and hydrogen ions, and the reduction reaction forwards. Sulfur dioxide is reduced to sulfur. What is the redox reaction here? Take note of the relative amounts of electrons gained and received. They are not balanced, as one puts it like that. Not as many electrons are given as taken in the form of the equation written here, so an adjustment needs making. And then please give the final answer for that. Did you notice that you should multiply each element within the top equation, the oxidation half reaction, by 2 so that the electrons are balanced, and that gives us a final redox reaction as shown here. And did you get the final answer of 0,31 volts for the electrode potential difference between the electrodes? Obviously, voltaic cells' use is as batteries to generate an electrical potential difference from a chemical reaction. But there are a variety of batteries, and we'll look at that in another set of videos. But one that I'd just like to draw attention to now, which is becoming quite important in modern day battery making, is a fuel cell. In a fuel cell, you continually input the electrolytes. That's why it's called a fuel cell, because it's like you're adding fuel continually. And here in this fuel cell, you add hydrogen, you add oxygen, and from this, you generate electricity by redox reactions happening between the hydrogen and water and oxygen and so on. And that only releases water, which is obviously clean emission. And so that is why fuel cells are being looked into as a potential environmentally friendly option of generating power.